very much, Serafiq. Thank you very much, Serafiq, for giving me the opportunity to present Mrs. Ibtissem Hdhiri, who is Tunisian. Currently, she is in position in Sciences and Technology Faculty in Gabes in Tunisia. She has also been in position in Saudi Arabia during several years. What can be said about Ibtissem Hdhiri? She has defended her PhD thesis in 2006 in Le Mans University here in France. I was her supervisor. She has worked on backward stochastic differential equations, are equations which mainly we find in mathematical finance. She has also worked on optimal switching and impulse control, and mainly the talk of today is related to impulse control. She has published several papers in this area in high-level mathematical journals. She becomes now a great expert in stochastic optimal control and backward stochastic differential equations. She has supervised several PhD theses, among the one by Helmi Zatra and also the one by Monia Karouf. Last year, she has defended her degree in France. We call this habilitation, in order to become full professor in Tunisia. So mainly, this is what can be said about Ibtissem. This is, I mean, short abstract. Now the title of the talk is Some Classes of Stochastic Impulse Control Problems. Yeah, it's to you.
Thank you very much, Said. Thank you to the organizers of this webinar. So I'm going to present some classes of stochastic impulse control problems in a Markovian framework, with emphasis in the problems we deal. I start by recalling the classical framework of stochastic impulse control and illustrate how the problem is modeled and how the optimal policy is characterized. Next, I will introduce the concept of delays in the impulse execution, and we will see how these delays affect the system dynamics and the optimal strategy. And finally, I consider the more general case where the size of the impulse can be chosen at the moment of execution and not the moment of decision. Let me begin with a general definition of stochastic control, which consists in controlling the behavior of a dynamic system, typically modeled by stochastic differential equation, in order to achieve a certain objective.
Sorry, Ibtissem.
Of course, right?
There seems to be some noises and echo in your audio, please. Some noises, some echo.
Maybe I'm moving.
Thank you.
It's better?
I think yes.
Okay, thank you. Okay, so it consists of controlling the behavior of a dynamic system in the presence of uncertainty in order to achieve a certain objective. When this objective is to maximize or to minimize a certain payoff function, that can be the total expected costs or rewards or profits, we speak about optimal stochastic control. This kind of control problems is based on some key elements. First, the state process A, which describes how the system evolves over time. It may contain also all the relevant information about the system at each date. Then it's Al-Khwarizmi, which can be finite or infinite, of course, depending on whether the problem is studied over fixed periods or in the long run. The control process, which represents the action taken by the decision maker or the controller, and the set of admissible, admissible strategy that contain the strategy that are at the same time mathematically defined and physically feasible. And finally, we specify an objective function which gathers all the costs and gains generated by both the state dynamics and the counter action. And then the goal is to optimize the objective over the admissible strategies. In standard continuous stochastic control, the controller acts on the system continuously in time. The control then is adjusted gradually and the effects reflected smoothly in the system. However, in impulse control, in the context of impulse control, actions are usually associated with important costs, and each intervention produces an instantaneous jump, as we see here, an instantaneous jump of the system behavior. And intervention can only occur at discrete time, tau n, and the size of each jump will be called Cn. It's a random variable that will be f tau n visible. So, as an illustrative example, we consider stock management application. Here, from one side, ordering too frequently may increase fixed costs, may increase costs that are fixed and additional expenses. From the other side, waiting too long to reorder can cause stockouts, lost sales, and customer dissatisfaction. So, impulse control helps find the optimal balance between these two risks. So, we have to decide when and how much to order so that costs are minimized while maintaining sufficient stock levels to satisfy demand.
Ibtissem, sorry. If your connection is stable, could you please try switching to another microphone or computer? Because there are a problem with the sound. It's not clear and there are some echo. Please, I'm sorry.
Consider a company. Let's consider a company generating pollution whose level is related to production and many external factors. So it's obviously stochastic. The company can intervene occasionally to reduce emissions, for example, by installing treatment measures. And each intervention is very costly. So it's important to decide both the optimal timing and the intensity of the action in order to balance production benefits with environmental costs. And hence, the best framework to model this situation is impulse control. We arrive now to the mathematical formulation. Let omega AP, FP be a complete probability space in which is defined Brownian motion B, whose completed filtration is denoted by F. Here, in this context, we are considering only a continuous model, and we define the following sets of processes. So we consider a sequence of stopping time, tau 0, tau 1, etc., representing the intervention times. At each intervention at tau n, the controller chooses an impulse of size Xn. So in that case, the Xn will be measurable with respect to the information at tau n. And the pair here, the double sequence delta, is said to be an impulse strategy. And the process, the controlled process L delta under strategy delta can be written in the following way. So it's the uncontrolled process to which we add the cumulative action of the controller. Here, the objective functional G of delta represents the expected utility of the cumulative rewards over time horizon. HEC is the instantaneous reward. And we integrate this instantaneous reward and then minus all the costs Psi of Xn. Typically here, the cost Psi of Xn is composed of a fixed part and a variable one, which depends on the size of the intervention. And this last structure is essential because it prevents infinite frequent intervention. Here we denote by A the set of admissible strategies, and by AN the set of admissible ones that allows at most to have n+1 intervention.
What do you mean by admissible strategies, please? A, the set of admissible.
Defined here. It's defined here. Oh, yes. Tau n are stopping time. It's a sequence, increasing sequence of stopping time, and Xn are random variable which are f tau n measurable. Here, the condition that the only condition that the tau n are lesser than capital T, and Xn are f tau n measurable. So this kind of strategy is said to be admissible. Okay, so our objective is to find an optimal strategy, delta star, that maximizes the functional G over the set of admissible strategies. If the underlying process is Markovian, we can use PDE techniques to solve the problem and characterize the value function through quasi-variational inequalities. However, in a general framework, when the process is not necessarily Markovian, the problem becomes more challenging because the value function depends on the whole path trajectory, and dynamic programming is no longer directly applicable. So in that case, we proposed an alternative probabilistic approach based on a Snell envelope of processes and backward stochastic differential equation. So let's recall the notion of Snell envelope of processes. If we have a process X which is CAD-lag and uniformly square integrable. So we can define its Snell envelope as the smallest CAD-lag F super martingale of class G that is greater than X, and it will be written in the following way. It's the essential supremum over all the stopping time after T of this conditional expectation. We have two properties of Snell envelope which are very interesting. If XCN are processes, CAD-lag processes of square integrable CAD-lag processes, such that XCN is increasing to X, so such is the Snell envelope of XCN, which will increase to a Snell envelope of X. And when X is upper semi-continuous, then its Snell envelope will be continuous. And the first time it reaches it will be optimal in the sense, in the following sense. So it relies the essential supremum over the set of stopping time in the expression of the Snell envelope. Our second tool is backward stochastic differential equation, which are stochastic differential equations for which the terminal value is given. And when the solution is constrained to be over a barrier, we speak about reflected backward stochastic differential equation. And in that case, a triple of processes y, z, and k is said to be the solution of the RBSD associated to the generator F and the barrier X if they satisfy the following equation. And the first component y admits the following characterization. So it can be written by means of Snell envelope of processes. So as we said before, if the barrier X is upper semi-continuous, then the process Y will be continuous. And we have the following comparison results, which allows us to compare the solution, the first component of the solution Y, once we can compare the coefficients of the backward and the barriers. Okay, and as I said before, the first component can be written by means of the Snell envelope of the following process, xt plus this integral. Okay, we move now to stochastic impulse control of in the general framework. Here we suppose that the state of the system is given by the following is the general process LG, and their word is written in the following way. So the decision variable here are the sequence tau n and xn. Tau n is an increasing sequence of stopping time, and xn, the condition the measurability condition here is xn is measurable with the information at tau n. Okay, here let D be the set of finite strategies. That is the strategy that doesn't allows us to have an infinite number of interventions. We can prove that the supremum over the set of admissible strategy and finite strategy coincides. And we construct the following scheme, iterative scheme, by means of stochastic differential equations. Here, to simplify, we consider stopping time nu and a random variable xc, which is f nu measurable. Y0 of nu xc will be the solution of the following non-reflected BSGs, which exists and is unique. And we construct the following system of equations. Here we have a system of reflected backward stochastic differential equation, which are interconnected. So we prove the existence and unicity of the solution of that kind of system, and the first component will be written in the following way. It admits the following representation, with here the barrier, which is defined as the maximum over u here is, I forget to say it, u is finite here, the maximum of the following quantity. Okay. In addition, we can prove that our scheme is increasing, and it's bounded by a constant. So we can speak about the limit process y. And after that, we prove that the y itself is well defined, is unique as the solution of our reflected backward stochastic differential equation, is bounded, and the barrier of this reflected backward stochastic differential equation is not L than O, which is the limit of the barrier of ON. Okay. So we succeed to write our process, our limit process, by means of Snell envelope. And when we succeed to prove the continuity of the process y, we can speak about the optimal strategy, which is written in the following way. We can prove that the strategy delta star, defined by tau n star and beta n star, tau k star here are the first time when y reaches O, and the beta star realizes the maximums over u in the expression of the process O. So we can prove that this strategy is optimal for the impulse control problem, and furthermore, the value of the problem is given by y0, 0, 0. Okay. So until here, we considered the problem when we decide to intervene, and we execute the intervention at the same time. But in a large class of application, the intervention requires a heavy preparatory work. So if we decide to intervene at tau, the action will be carried out at tau plus a lapse of time, which we call delay. Donc, here the delay for us will be fixed positive real delta. So when we decide at tau n, the execution will be at tau n plus delta, and in that case, the admissible strategy will be a double sequence tau n and xn. Tau n is a non-decreasing sequence of stopping time which are smaller than t minus delta here, and the magnitude xn will be a random variable which is measurable with respect to the moment of decision, that is at f tau n. And the controlled process can be written in the following way, with LT to which we add all the action carried out at tau n plus delta. And the total expected yield, it will be written in the following way. And as usual, we aim to find an optimal strategy for this problem. So to do it, we construct an iterative scheme by means backward stochastic differential equations. Here, the barrier in the expression with of the barrier here, we use the conditional expectation in order to guarantee the measurability of key n with respect to f tau n. And we prove that this scheme is well defined, is unique and well defined, and have some interesting properties. And we can construct a strategy delta n star, which is optimal for the impulse control problem using a similar reasoning as before. So we can prove that this problem admits an optimal strategy delta n star, and the value is given by y0 and 0, 0. Of course, here, since the actions are carried out after a delay delta, two consecutive actions must be separated at least by delta, and then we cannot have an infinite number of intervention. Here we have a bounded number of intervention, which is the length of the whole interval divided by delta, by the delay delta. And then the general problem here will be resolved by means of y0 capital N. Here we don't need to go to use the limit process. Okay. We move now to the delayed impulse control problem when impulses are decided at the execution time. Until now, we have supposed that the size of intervention is determined at the decision time, but we know that during the delay, new information may become available, and the state of the system may evolve. So this naturally leads to a more flexible formulation in which the intervention time is chosen first. Then after that, we choose the size of the impulse at the execution time. And in that case, the optimal strategy will be defined in the following way. It has to verify these 2 points. Here we have at least a lapse of time delta between 2 consecutive actions, and the Cn here, the size of impulse will be f to n plus delta measurable. The set U is a finite set of RL, and the total expected reward is written in the following way. Here U is the utility function. When it equals the identity, so we are speaking about risk neutral case, and when it's of exponential type, we're speaking about risk sensitive case. For the risk neutral case, so the G of delta is written like this, and we suppose that H is bounded by progressive function gamma of t, and psi, here we are working with the elements of RL, donc psi of A ici, here will be positive. And our iterative scheme can be written as follows. Here we cannot work directly using the random variables to avoid the problem of measurability. So we are working with real or with vector values. After that, we will move to the general case. So we define yn in the following way by means of reflected stochastic differential equations, backward stochastic differential equations, and we prove the existence of the solution. Okay. We prove also that the scheme is convergent, and between t minus delta and t, the process yn coincides with the barrier ON. After that, we defined the process yn of xi for xi for when xi is f2 random measurable random variable, and tau is stopping time. So after stopping time tau, we defined yn, zn, kn, and on in the following way. So donc here xi take the value a, and we prove that these processes are well defined. They are increasing. The sequence yn is increasing, and it allows us to have to resolve the problem of stochastic impulse control problem. And as before, we don't need to consider the limit process, because it's sufficient to have the result for the set of bounded strategy. So the general problem is resolved by means of the process y capital N of 0. Okay, now for the risk sensitive case, as I said, here the utility function is of exponential type. Here the sign of theta can be positive or negative. It depends on the behavior of the controller. He can be risk-seeking or risk-averse. And without loss of generality, we can assume that the theta equals 1. And in that case, using backwards stochastic differential equation and Snell envelope, here we use only Snell envelope processes. I'm sorry, to prove that y0n is the value of the impulse control, and we construct an optimal strategy denoted by delta capital N. Okay, so here is the scheme. Okay. We move now to the infinite horizon case. In that case, we are considering the delayed stochastic impulse control problem when actions are decided at the execution. So here we are working with infinite horizon, and we define the following sets of processes. Here we have an additional difficulty because we are not, it's not sufficient to have a bounded number of intervention, since we are working between 0 and plus infinity. So we have to consider the general case and to prove the regularity of the limit processes. We denote by A infinity the set of admissible strategy and AN. the set of admissible strategy having at most n intervention. And the payoff is written in the following way. U can be the identity or exponential. And we suppose that the coefficient G here is bounded by a progressive process gamma, verifying the following condition. We construct an iterative scheme based on infinite horizon backward stochastic differential equation. So we use here non-reflected BSGE and here reflected ones with the process, the barrier process defined in the following way. Of course, here we need that the Cn will be f tau n plus delta measurable. So we put the maximum inside the conditional expectation. Okay, we prove the existence and unicity of the solution. And after that, we prove also that the scheme is increasing and bounded, so we can speak about the limit process Y. And after that, we prove that this process is continuous. And we prove also the existence of the an optimal strategy, delta star infinity, for the infinite horizon stochastic impulse control that satisfies the following condition. And of course, the value of the problem will be given by Y0 of 0. And here are some references for this talk. Thank you very much.
Saeed?
Yes, I'm here.
Yes. Do you hear me?
Yes.
Okay, good.
So other questions, if it's for me, to ask for the audience who has a question. Yeah. So who has a question?
Yes, I have a question, two questions. The first question, if you can go to slide 27, Ibtissem, please. For the strategy delta n star 27.
Yes.
Okay. How you can choose explicitly the strategy delta n star?
It will be the tau n star will be the intersection. So you see here we have the yn and here the barrier on. The tau n star will be the intersection of yn with its barriers, and the beta n star will be the random variables that verifies the maximum here.
And there is only one strategy, or there are many strategies which optimize?
Here we construct only one strategy. We guarantee the unicity of beta star. We construct it to be unique.
Okay.
Unique star.
Mm-hmm. And it is the best strategy from all strategies.
Yes, we prove is that it's the optimal one. Yes.
Okay. Okay. For slide 32.
32.
Here, ONTNA, OTNA is free of delta of the window delta or not? The big
Here?
O, yes, the big O of TNA. Yes, is free of delta, or it depends on delta?
No, there is no delta here. A is in RL, the vector.
Okay, there is no delta at right here, at right hand.
The O is here.
Okay, it depends on delta, sir. And
As
how
it's written here, no, it doesn't depend on delta. There is no delta here.
at right there is delta. Integral from t to minimum. Okay.
Sorry, here, yes?
Yes. At the beginning of the expected value, the integral from t to t plus delta maximum with or minimum with t. So
You're speaking about the delay here.
yes, delay, yes.
Okay, I'm sorry.
Yeah.
The big delta, yes, it depends on the delay.
Okay, and how you choose this delay?
We suppose that it's a fixed delay.
Okay, so it is given the delay.
Yes.
I have a more general question. The second part cannot be deduced from the first part by truncation or by letting capital T goes to plus infinity. Cannot deduce the result of the second part from the first by letting T goes to plus infinity, or there are some problems.
Now it's not the same equations.
The problem in the second part, it is not for T equal to plus infinity, no? Capital T. In the second part of your talk.
You're speaking about the infinite time horizon?
Yes. Yes, this one.
Yes.
So here it is not the same problem as the first part, but capital T equals to plus infinity, no?
Asymptotically, it's not the same thing. For example, here we suppose that the process is continuous at plus infinity if the limit exists.
Mm-hmm.
So it's not really the same thing.
Okay. So we have that the process have a finite limit in when T goes to plus infinity. Okay.
Mm-hmm.
The last question, could you elaborate on how the impulse control problem is transformed into several stopping problems?
Into several?
Stopping problems.
Yes. Here we have combined stochastic control problem and optimal stopping. Yes, it can be divided into several optimal stopping problem, but for the XCN, it's a control problem, not necessarily optimal stopping. So we have both features.
Okay. Thank you, Ibtissem, for this nice talk.
Thank you, Sir Rafiq. Who has another question? Yeah, if you allow me, I have two questions. The first one is related to the sign of psi.
Yes.
Okay, mainly you have said that psi is positive, which is a cost. But sometimes it happened, especially in the economic sphere, when we make an impulse, we get subsidies, which means that psi in this case is negative in such a way that minus psi will be positive.
Yes.
So what about this case?
It can be relaxed. It can be relaxed to this case. I think you have done some work that is not far from this.
Yeah, in the impulse, I mean the switching problem, where I mean mainly we have finite number, I mean, of modes to which we can switch, and then mainly everything is finite, and then there are not some difficulties which arise from measurability, especially when we take the supremum or the suprema or infima of stochastic processes. They still, if you take the supremum of two continuous functions, it's continuous function. But if you take the supremum of an infinite number of continuous functions, it's no longer continuous. It's lower semi-continuous, and then you can face this kind of problem. Therefore, I'm not sure that we can make transposition of the what happens in the switching problem to the impulse control problem, where basically when you take the maxima, they are rather in infinite, uh, yeah, infinite.
I haven't considered that.
Yeah.
Okay.
Okay. Another question is related to the utility functions.
Yes.
You have worked especially mainly with the exponential utility function. So is it possible to consider other utility functions, for example, the power utility function?
Yes, why not? Why it can be, we can consider it.
Oh, and then you can go ahead.
I think yes.
So we can write all those, equations in such a way that it's possible to solve the problem.
So here we have to choose the good system of
Because
equations.
the exponentiality function is specific. It has some specific properties which make that the problem can be considered. But if it's power utility function, in this
I
case,
think that even I haven't considered, but I think that even for utility power, it can be feasible. I have to see it.
okay, thank you. That's all for me. Yeah. Are there other questions?
Yes, please. I have a question about the delay capital delta. Could you clarify the practical motivation for introducing a fixed delay delta between decision and execution? And in which application does this naturally arise?
Okay, in fact, in some application, we need to buy, for example, some goods and wait that they arrive, or we have to we have an action that needs a preparatory work. It can't be carried out instantly, immediately.
Okay,
So
good.
it's motivated by this.
Okay, good. So it is not more realistic to choose delta as a random and not deterministic.
Yes, yes, it's more realistic, but
okay,
it will be in future work.
So there are some difficulties to consider delta as random.
Yes, it changes because we have to enlarge the filtration to make to the random variable have to be stopping time in order to can work with them.
Okay, so delta must be sequence delta n of IID random variables, maybe. Okay. Okay, thank you.
Thank you.
Yeah, just to say that, in energy market, just in order, so since I get involved in all those subjects, so in energy market, for example, when you buy, say, oil, or you buy gas, you order today, but the delivery is not made instantaneously. It is made, say, after a while, 1 week or day later. This is mainly the motivation of considering delay, and it could happen that the the quantity of that you ask for is fixed when the order is made, but sometimes the quantity that you get is decided at the after a delay. This is mainly the second. This is mainly the second third part of her talk.
Okay.
Yeah, that's all for me. Yeah.
Okay.
Maybe I have a question.
Yes, I'll
Can
start.
I? Okay, thank you. Can you go back to the definition of the strategy?
In which part?
The first time when you introduced the notion
Okay.
delta.
Here.
In the definition, there was a definition based on a set of the delta strategy. I think before this, or maybe after.
Maybe here.
I don't know.
Not sure.
Maybe before.
Before. There is no strategy before.
Okay, maybe after. So like here, this one. The set D. I mean the set D. Where you define the set D here. The set strategy. I don't know. I don't see what's the delta doesn't appear in the condition. I just want to understand the set of delta such that P of 2 tau n less than T. There is no delta in the assumption here.
So here we prove that the supremum over A and delta are the same.
No,
I see, but what's
And we are concerned with the supremum of A over A, but we can work only using the supremum over G.
yeah? I mean where delta is involved in the equation in which we define D. Delta is the set of G, the set of
The
delta
set
in A
of
such
tau
that
n tau n. Delta is tau n Cn.
Delta is the
Tau n
strategy.
is the intervention time.
Okay. Thank you very much.
And here for all n or for some n? Probability tau n less
For every n.
for all n. Okay.
Yes.
Okay.
Yeah, this condition means that omega by omega, we do only a finite number of impulses, which if omega, there are days, it means that today we make only say 100 impulses and tomorrow we'll make only 10. And this, sorry, Ibtissem, because as I told you, I get involved
No
in these
problem.
works. So yeah, I mean, when you are going to show that the strategy is optimal, you need this characterization. You need the fact that I mean the supremum over A is nothing else but the supremum over delta, because in order to take the limit and so on. Yeah, maybe it's I mean she did not go into details, but still that you need this.
Okay. Can you clarify again the simulation that you have done, Ibtissem, please, and show us where is capital delta and the simulation at the beginning of the talk. Simulation. Yes. So okay.
So in green here, the discrete decision time, tau n, and in red, tau n plus delta. Just to motivate the control problem with delay.
Okay. Okay, thank you. Thank you for me.
That's all also for me. Are there other questions? Yeah, it's up to you, Sir Rafiq.
Thank you, Saeed, and thank you,
Thank you very
Ibtissem, for
much
this nice talk.
for inviting me.
And see you, inshallah, after 2 weeks with another talk. Bye.
Thank you very much.
Thank you.
Yeah, hopefully.